We want to talk about images formed by refraction, and we'll start with like a piece of glass. That might be water, and that's air. We got a fish over here. We're looking, or it might be a penny inside a block of glass. Whatever, the light from the object is going to be refracted at the surface, and since we're assuming going from slow to fast, it's refracted away from the normal. That'll give us a relationship between the indices of refraction in P and Q. Notice it's a virtual image, and we've said with mirrors, virtual images are negative. So anyway, we just, there's theta 1, theta 2. We'll just apply Snell's law. We're going to use small angles for spherical lenses, and so we'll make the approximation sine and tangent are roughly the same. And then if we do tangent of theta 1, for example, opposite would be the height of our object. This would be the height of our object over the distance P for that triangle. And that would be N2 times the tangent of theta 2. Theta 2 is here, and that means it would be from this line to the dotted line. So we have this triangle, if you will, and so, well, I guess it would be over here. The opposite of that would still be the height, h prime, which are equal, as you can see in this diagram, and then the distance would be q. But it's virtual, so since we want these to be equal, we have to get rid of that negative in the q, so we put a negative there. You rearrange those and say that h and h prime are equal, and you get a relationship showing that q depends on the indices of refraction and p. Now we're going to use that relationship. I think there may be one homework problem that uses that, but what we're going to do is we're going to now think about a curved surface. So this would be like the insect in the glass paperweight, the spherical paperweight. And what we have to do, well, we didn't really do the whole diagram here, but we have to go through that same process and do the refraction there. Remember we said it's refraction relative to the tangent line. That's how you get your angles. And you go through a similar process as we did there, and you get a relationship between the radius now and the two indices of refraction in P and Q. That derivation is a little bit longer, and it's inside. It's in the book if you want to look in the details of that. But the first one, the simple we did, showed how N1 and N2. So the difference, it looks a lot like the mirror equation, only it's got the N1 and N2 in it. Again, we can have real or virtual images depending on where things are. What we're going to do now is think about a lens, which is some curved glass, again, typically spherical, so we're going to have radii. And we're going to apply this equation for refraction at a surface twice. So we have the first object, the rays are refracted. We've got 1 and air. That's going to form an image. That image becomes the object for the second lens, which is refracted. And that'll make us a final image. Again, the details on that are quite long, so I didn't put them in the slides, but they are in the textbook if you want to read through that. And we're going to have a final relationship between our initial object distance, P1, and our final image distance, and it's going to involve the indices of refraction. N1 is just air, N2 is our glass, so this equation simply becomes this equation. Again, we've got and that has to be applied to the second image, to the second one. That was for the first side. This is for the second side. You apply it, and now you swap 1 and 2 and combine those, and we end up with that equation, which in terms of the first image, remember the first image is the second object. And then we're going to, and because of that, then P2 becomes minus Q plus T. Again, a little bit of algebra to do, but what we end up with is called the lens maker's equation. And it looks a lot like the mirror equation. 1 over P, 1 over Q. The algebra gives us an n minus 1, because remember, air's on one side, glass on the other. And it's the difference in the two radii, 1 over R1 minus 1 over R2. So 1 over that will be our focal length. So that'll be our focal length. So the focal length depends on both the radii of your curved surfaces and your index of refraction. So it's a bit more complicated. And this is also what we call the thin lens equation, because we've ignored the thickness. Basically, we let it go to 0. Now, if you look back earlier. And that's the one we want to work with. We do the magnification, basically h prime over h. It's going to come out to be the same one we had for the mirror equation. Same conventions. P is real, real object. Q is positive when it's real, negative when it's virtual. Instead of front and back, I just tend to think about those when I work problems. So let's look at array diagram. How are we going to do array diagram? Well, here's an example. There's a demo we like to do. I do in class sometimes. And so I've got parallel coming in. There's my lens. This one is what we'll call biconvex. It's a converging lens. Really what we want to say is converging lens, diverging lens, converging mirror, diverging mirror is more descriptive than the concave and convex, especially for lenses, because it takes both surfaces. But anyway, parallel light coming in is then focused at the focal point. And that focal point is 1 over f is, n minus 1, 1 over r minus 1 over r. It's a little more complicated. They may have you calculate it once, but mostly we're just doing the 1 over p, 1 over q, 1 over f. So parallel light comes in at a focal point, or light coming from the focal point goes out parallel. And we can use that to do our ray diagrams. There's the diverging lens, thinner in the middle, the converging lens thicker in the middle, and the rays are bent away from the normal, from the focal point, or if they come in toward the focal point, then they're bent toward, they come out parallel. There's some different lenses, biconvex, and again, just like for the mirror, when we work problems, we made the radius positive or focal length positive for a converging and negative for a diverging. Same thing here. We'll have a positive focal length for a converging lens, negative focal length for a diverging lens, and I'll work several examples so you'll know how to do those. More thin lenses, those are all diverging. All right, here's our ray diagram, and we've got the app on that too. So let's go look at that simulation. There's a converging lens. We're going to use 3 rays. We're going to use the ray that comes in and then is bent through the focal point. We're going to use the one that goes through the center of the lens, which is approximately the center of each curvature. That one will be undeflected, so where they cross, we get an actual image. Now, this is a real image, and you couldn't use the 3rd ray. You really only need 2. Doing it by hand, I usually only do 2 because it's hard to do it by scale to get the 3rd one to come out the same. But when I'm very far away, then I get a real image. As I come in toward the focal point, notice the image goes further and further out, and then once we cross that focal point, you can't see it, but it begins to come back in because it goes virtual. It goes virtual. Now it's virtual, and it comes back. Notice that real images on lenses are inverted, virtual images are not. And notice the difference between this and the mirror. That's where people get confused. The mirror ray, the ray bounces off the mirror. Here it goes through the lens. And I'll do some examples of that in some of the homework as we work through some of those homework problems. So here's the one where we get a virtual image. Again, the same 2 rays, or 3, but I usually use the center one and this one. I like those the best, generally speaking. But you go through, and you notice you go straight through and through the focal. They diverge, so you have to backtrack them. And so where you have to extend the rays, those are virtual rays, and you have a virtual image. Virtual image upright. So this one would actually have a magnification that's positive, bigger than 1, and a Q that's negative. There's another ray diagram and a summary. Now we have aberrations for for mirrors because they're spheres. We also have an aberration for lenses because, as you remember, the index of refraction is often a function of color. So in the real world, what will happen is for the cheap lens, we'll blur the image because the focal lengths are different for each point, for each color. So there's some where you see that. It's called chromatic aberration. And that's just due to the fact, as we can see here, each color is going to have a slightly different focal point. Alrighty, that's thin lenses. I'm trying to keep these videos fairly short. I'll work some examples and give you some and show you how to do some ray traces in the problems. See you on the next video.